yield lines special cases. This video deals with a circular slab loaded or partially loaded with a distributed load. You see here a circular slab simply supported on the edges with a diameter r, and it's loaded partially by uniform distributed load Q. The total load on the slab is QP small r squared. And the small r is of course between 0 and r. Now we will use the yield line method, and for this we are looking first for the axis of rotation. So I take one part of the slab, and the axis of rotation is in a point on the circumference of the slab, because I want to make a mechanism of pieces of slab moving around rotation axis. So it means it's a line like this on each point. So you have an infinite number of rotation axes. So let's take 3 of them to demonstrate. The yield lines are now connected by when 2 rotation axes cross, then between those 2 cross, the yield line will be there. So it means that when we have here 2 rotation axes on this side, then on the other side of the slab, for instance here and then there, so you can draw now a line where the yield line should be, which is perpendicular to the circumference. Then we can draw the 2 yield lines. So we'll use this principle for the whole circumference, and we draw not all, because that's not possible, but some of the yield lines. So there you go. Now I've taken a couple of yield lines, and it's always the same mechanism. The axis of rotation is a straight line at one point of the circle, and we have in total an infinite number of yield lines. So now we will calculate the work done by the external loads, and to do so, we need to calculate the mean deflection. This is the slab. It's simply supported on both sides. It has an axis of rotation of theta, sorry, and deflection units of delta. We take now the right-hand side. The theta, of course, is delta over r for small thetas. It's in fact the tangents of theta is delta over r, but we are working with small angles. And we see this portion of the load with a radius of r, small r. Delta 1 is the deflection on this side, on the skirt of the load, and delta m is the mean deflection of that portion. So we see easily that the tangents of theta is given by delta 1 divided by r minus r, and it should be equal to delta divided by r. So now we have a value for delta 1 in respect to the unit deflection, and delta m is then the first. You have a global deflection of delta 1, so that delta 1 plus what's left is the mean deflection of a triangle, which is 1/3 of course the delta minus the delta 1. This portion, it's a triangle. You can also see it when you have a yield line here, and just next to it there's another yield line. So you will see these are all triangles, and we have seen in the previous videos that the mean deflection of a triangle is 1/3 of the unit deflection. So delta m, the mean deflection, is equal to this formula. You can of course calculated by using integrals. But this method is quick, it's faster. It goes. So now we will calculate the virtual work done by the external forces, which is of course the total load area or the total load, which is Q pi r squared, multiplied by the mean deflection, delta m. The mean deflection was given by this formula, so now we can substitute it in the work done for the external forces. We calculate now the work done by the internal forces, so that means that we have to project the yield line to the axis of rotation, but because we have an infinite number of yield lines, it means that the projected yield lines is equal to the circumference of the circle. So it's 2pr. That's bending moment m times 2pr over the angle of rotation, which is of course the delta divided by this distance, it's r. Now we make those E and D equal and get m out of the formula, and this is the bending moment or the maximum bending moment in the slab due to a partially loaded distributed load. We can now look at different cases. This was what we have calculated just now. Now we can look when the slab is loaded by now we can look at the situation where the whole slab is loaded. So small r is equal to big R. So if you substitute it in this equation, you have cube d squared over 24. And another special case is when R is approaching 0, so it's for a point load. Then if you have a point load, and the point load in fact is Q P R squared, we put it in this formula and you find that the value is then P over 2P. 2 pi, sorry, P over 2 pi. This looks strange because if we say R is approaching 0, it means that M is 0. You have R there and R there. So let's see how did we come to this result. We can now look at the general formula that we have found for a partially distributed load. And we say that P, the point load, in fact, it's not a point load, but a very concentrated region of load with E equals to Q pi R squared. And R is small. So we concentrate all the loads in a small dot. Then we substitute P and we got this formula. And now you see when for the limit for R very small, that this will be 0 or can be neglected through the unity, or m is p over 2 pi. So that's in the limit when r is very small. Now, if we don't believe this result, then we can say, okay, let's redo the calculation. We will calculate the work done by the external force. So it's the point load P times the deflection delta. The work done by the internal forces is then, like we've seen, the bending moment M projected to the axis of rotation, which is 2pr, and the angle of rotation is delta over r. We get from E equals D, we get M, bending moment, and M is P divided by 2 pi. So we can be confident this result corresponds, so it's okay. But looking at this formula, it's something very strange. It's a bending moment independent of the radius of the flap. So in first sense, we would say this is not possible. There's something wrong. But if you think about the following, that is that the work done by the internal forces is independent of R. That's why this is happening. So it means that because there are so many yield lines, when every yield line is yielding, then the resistance, if I can call it like that, is proportional to something squared. So it's proportional to a surface. And that's why the bending moment, and the bending moment is also proportional to r squared. So that's why those two cancel each other out. But the best explanation is that the work done by the internal forces are independent of the radius. That's why the bending moment is independent of the radius.